Hello, everyone. This is Alex, and welcome to the mathleague.org YouTube channel. We'll be talking about problem 10 from the January 2021 middle school test 12114. Okay, so we're given that Belle's highest score on an arcade game is a positive integer less than 1,000. Let's go ahead and let's call this x, right? So the problem says when she squares her highest score and divides the result by 91, the remainder is 79. So x squared, we'll ignore that part about the third greatest possible value for now. Let's just focus on what it means to square a number and have it leave a remainder of 79 when that square is divided by 91. So we call Belle's score x. That means x squared, I'm going to write this down now, leaves a remainder of 79 when divided by 91. Well, the standard notation for that is x squared is what we say congruent to 79 mod 91. And sometimes we just write it in parentheses like that. So x squared leaves a remainder of 79 when divided by 91. X squared is 79 mod 91. Okay, so what can we do with that? Do we know how to take square roots in an unfamiliar modulus like 91? Or do we know how to take square roots in any modulo system? Are we willing to bash out all 91 possible values for x in the mod 91 system from 0 to 90? Almost certainly not. So let's go with a different approach here. Can we perhaps look at the factors of 91 and see if we can get some other divisibility or congruence conditions that are much easier to work with? Well, yes, we can. If we look at 91 not as 91, but as 13 times 7, well, 13 and 7 are both prime. And they're definitely relatively prime to each other because they share a common factor of 1 only. So, we can apply what's known as the Chinese remainder theorem to look at x squared mod 13 and mod 7 instead of mod 91. Now, what is the Chinese remainder theorem? Well, it tells us that for any two relatively prime positive integers, m and n, positive integers relatively prime, in other words, their GCD is 1, their greatest common divisor. If some number x is congruent to a mod m and b mod n, where, of course, we're assuming that a is between 0 and m minus 1 inclusive, and b is between 0 and n minus 1 inclusive, then there exists a unique c such that x is congruent to c mod m times n. So, for example, if we wanted to find x mod 6, given that it was congruent to 1 mod 2 and to 2 mod 3, well, what Chinese remainder theorem does is it guarantees that this mod 6 value actually exists. And indeed, we can find out that it's 5 mod 6 because 2 mod 6 doesn't work because of the 1 mod 2 condition. That means it's odd, and no number that's 2 mod 6 is odd. While this doesn't directly give an answer to our predicament, we can see that we can now bash out values mod 91 given the values mod 13 and mod 7. It's an existence theorem, not a constructive one, because it doesn't tell us what the mod 91 value actually is. But still, we can apply it with mod 13 and mod 7, right? Well, let's see. It's probably best to go back to thinking about it in just a simpler way in terms of remainder instead of modulo, and think about what it means more intuitively, right? So if a number leaves a remainder of 79 when divided by 91, then what remainder does it leave when divided by 13? So let's simplify this as much as possible. And we'll ask instead, okay, what remainder does 79 itself, just the number 79, leave when divided by 13? Well, that's just 1. So our x squared should be 1 mod 13. What about 7? 79 divided by 7, the remainder is 2. So x squared is 2 mod 7, and now we can start to make some headway on figuring out what our values of x should look like. Okay, so let's start with the first of these two congruences, the x squared equals 1 mod 13 and 2 mod 7, right, that we've just discovered. So from x squared equals, or congruent to 1 mod 13, can we figure out what x could be mod 13? Well, yes, we can. Now, we could just bash out all 13 possibilities from 0 to 12, of course, but do we have any better ideas? Let's see. 13 is prime, right? So if we want to skip doing as much work as possible, maybe let's look around at whatever else we have in our toolbox. So what do we know about prime moduli? Well, prime numbers in general, nothing divides them except 1 in themselves, right? Now, what if instead of x squared equals 1 mod 13, we wrote x squared minus 1 equals 0 mod 13, subtracting 1 from both sides, right? Now we're getting somewhere because we know exactly what to do with that x squared minus 1 guy, right? That's just the difference of squares. That's x plus 1 times x minus 1 is 0 mod 13. So we're going to get x equals, well, minus 1, that's 12, and 1 mod 13. Because, you know, one of those factors has to be a multiple of 13 because 13 is prime. So now both of them can't be multiples of 13 at the same time, so we know we're done. X can only be 1 or 12 mod 13. Cool. So we've got the first part down. And I'm going to write this over here. Same thing for x squared equals 2 mod 7, right? But wait, we don't know how to factor x squared minus 2. We can't just subtract 2 from both sides like we did before. It is small enough that we can just bash it out. So we'll just go through x equals 0 through 6. So let's see what happens. Well, 0 is obviously not going to work. Is 1 squared equal to 2 mod 7? No, it's just 1. Is 2 squared equal to 2 mod 7? No, again, it's 4. How about 3 squared? Well, yeah, that's 9. 2 mod 7, sure. 4, 16, that's 2 mod 7. 5, 25, 4 mod 7, so no. 6, 36, so 1 mod 7, nope, not that one either. All right, so it looks like 3 and 4 are the values mod 7 that when squared give back 2 mod 7, meaning our x has to be 3 or 4 mod 7, right? Now, finally, we can start putting all that together. We found out that x is 1 or 12 mod 13, and that it's also 3 or 4 mod 7. So I'm going to go ahead and just kind of erase that part. Or not that part, actually. Let's go ahead and put this in the middle. X is either 1 or 12 mod 13 and either 3 or 4 mod 7, right? So this is where Chinese remainder theorem comes in to find out what it is mod 91, because that's ultimately what we're looking for. But again, it won't really tell us what the actual values are. So I'm afraid the theorem itself isn't really going to do us much good there. But the numbers are thankfully small enough to where we can really just bash. And there's 4 cases to cover here, so we'll just go through them all. So case 1 is 1 mod 13 and 3 mod 7. Well, we can check the 13s. So we can start off at 1. That's not going to work. But we can go up by 13 every time. So 14, no, that's not 3 mod 7. That's 0 mod 7. 27, no, that's, 6 mod 7. 40, no, that's 5 mod 7. 53, no, 4 mod 7. 66, aha. Wait, yes. In fact, 66 is both congruent to 1 mod 13 and to 3 mod 7, right? So x can be congruent to 66 mod 91. Now we'll repeat this for cases 2, 3, and 4. So case 2 is 1 mod 13 to 4 mod 7. Well, we've already done the work for 1 mod 13, so we can just go back and take a look at our list. 1, 14, 27, 40, 53 works because that's 4 mod 7. X is 53 mod 91. Now, case 3 is going to be 12 mod 13. You can repeat this for 12 mod 13, 3 mod 7. That's going to be 38 mod 91. And case 4 is 12 mod 13 and 4 mod 7. That's going to be 25 mod 91. Okay, so 25 is our guy for that last case. And at last, we can finish solving the problem. Now, remember, looking past the problem, it says, what is the third greatest possible value of Belle's highest square? Third greatest. All right, so we really kind of want to work backwards, going backwards from 1,000. So what's a multiple of 91 that's close to 1,000? Well, that times 10, that's 910. That's close enough, right? Now, if we add 91 to that one more time, we'll get 1,001, which is too much. So 910 is actually the best we can do. So now all we have to do is add 25, 38, 53, and 66 to those guys. And I'm going to go ahead and erase this. We'll get largest possible values in descending order. Well, 910 plus 66, that's 976. And then you have plus 53, 963, plus 38, 948, plus 25, 935. And what's the third largest of those? Well, it's 948. So 948 is the third highest possible score that Belle could have gotten, and we are done.
Hi, everybody. This is Tim. Hope you're enjoying our videos. If so, you know what to do. Like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.